Thank you, everybody, for joining this webinar. And good morning, good afternoon, or good evening to you, wherever you're listening and watching. My name is Harold Bornfleth, and I'm responsible for the Besa product portfolio. Today, I'm going to speak about time frequency and connectivity analysis with Besa. I'm joined also by my colleague, Robert Spangler, who is somewhere nearby and will assist with questions and answers during this webinar. The schedule for today looks like this. First of all, we will walk through a bit of theoretical background of time frequency and connectivity analysis. I will then venture into an actual case of connectivity analysis, first for the case of a single subject, and then also looking at how to approach the analysis of a group of subjects using Besa tools. And a disclaimer, I will be demonstrating some brand new features using our beta version of Besa Connectivity 2.0, which is not actually on the market yet. However, it will be released shortly and can already be ordered. Altogether, I expect this webinar to last for between 45 minutes and 1 hour. And please, throughout the presentation, feel free to send in your questions. Simply use the available questions and chat boxes on your screen. We will pick up all your contributions to the discussion, and Robert and I will try to answer them all at the end of the session. I think I'm going to switch my video off so we can concentrate on the presentation on the screen. So, first of all, why time frequency decomposition and connectivity analysis? First, let us look at normal brain function. Brain regions with specialized neuron assemblies need to work together to achieve certain tasks, for example, multisensory integration. This can be achieved via synchronous oscillations, as, for example, reported by Singer and others, and many others confirmed these findings. Also, we have many brain networks now known that play a role for various tasks. We have the dorsal attention network, ventral attention network, frontal-parietal task control network, default mode network, and others. A recent development was that brain age analysis became more popular, and this is usually done using resting state connectivity analysis that can reveal connectivity changes. And also in pathological brain function, we find sometimes that frequency activity patterns are changed. So typically frequency rhythms are slowing down with age. In other pathological situations like epilepsy, we can look for high frequency oscillations, etc. So all these are to do with rhythms and oscillations. And in also pathological cases, network connectivity may be altered. In order to find and analyze these phenomena, we need some ingredients. So first of all, the time frequency decomposition. This can tell us at what frequency oscillations occur at which time, for example, related to a stimulus. And the next ingredient is then a connectivity measure, which allows us to extract the degree of functional or effective connectivity between channels. This can look like this example here. So again, we have a time frequency display here, but now it shows us at what time and at what frequency a certain degree of connectivity between a channel pair exists. Yeah, talking about channels, another ingredient that is highly useful in this analysis pipeline is the disentanglement of volume conduction effects from the actual synchrony effects. This can mean moving from sensor level analysis that's done on the surface, like this example up here, to brain level or source level analysis that we would actually advocate here. So going back to the time frequency decomposition, what we see here is we call it temporal spectral evolution of time frequency data. That means how does the activity evolve over time? Does it get stronger or weaker? And yeah, one thing maybe, by the way, we should talk about, is it even important if I do a time frequency decomposition first and then average, or can I do it the other way around? So let's just have a little side look at this scenario. So say I do a time frequency decomposition over all my trials and then average them together, and it would look, for example, like this, or if I scale it up, it'll look like on the right side. And if I do the other way, so I first average my data and then do time frequency analysis, then I can see a somewhat different spectrum. And particularly, you can see that in the upper case, I still have some frequency activity at higher frequencies that's left, for example, here in the gamma band. And this is actually a very, very real effect that I can also see in the temporal spectral evolution plot. So something that really has a gamma activity that I can detect if I do first do the time frequency decomposition and then average. But if I do it the other way around, then the averaging will already cancel out my high frequency activities because they're not strictly locked to the stimulus. So I will never be able to analyze them. Or to turn the whole thing around, not only does time frequency analysis give me a rundown of the frequency content of my data at any given time, it even reveals relevant signal that's related to the stimulus, but not necessarily perfectly time locked. Right, how do we compute it then? There are various different ways. The most popular one maybe is the Morley wavelet, which is, I think the popular choice. It has two main parameters. That's the oscillation parameter, which decides on the number of oscillations in the wavelet, and the length parameter, which is about the overall length of the wavelet. The formula at the bottom and the plots on the right show the Mexican hat wavelet. And this wavelet only has a length parameter. The number of oscillations is fixed here. So you can see in these plots on the right that the left of these templates will pick up a higher frequency than the right one. For each frequency of interest, in fact, there is an optimized template. There are a few example Morley wavelets that you can see here. So we can see the number of oscillations varying from the left to the right. So we start with 3 oscillations, then 5, then 7. And obviously, this has got quite an impact on the general wavelet shape. However, the top row here shows us the other parameters, so the length of 3, and the bottom row has a length of 5. And we can conclude, I think, that changing the length does not have such a big impact on the actual wavelet shape compared to changing the oscillation parameter. Also, each wavelet comes with a real part and an imaginary part. These two plots here show examples for Morley wavelet and Mexican hat wavelet, showing the real and imaginary parts. And the fact that we have these two parts is super useful because that allows us to compute not just the amplitude, but also the phase of our waveform. Another way of decomposing data into time frequency components is the complex demodulation, which uses the beat frequency phenomenon. So this is done by first multiplying the signal with a sine or cosine wave of the expected frequency. And if my signal has a frequency similar to that frequency of interest, then this will result in a beat frequency. That is just the difference between the two. And we can filter out this one by applying a low-pass filter after the fact. And the third method of doing it is what we call multi-taper. And this provides better estimates at high frequencies in noisy conditions compared to other methods. So to do this, we have a bunch of orthogonal DPSS tapers, which we then multiply element-wise with the signal. And then we compute a short Fourier transform, and finally apply a weighted average, which can be optimized for each frequency of interest. And that gives us the multi-taper transformation. Whichever method I choose, there is a trade-off between the time resolution that I can achieve and the frequency resolution. Just like in quantum mechanics, between position and impulse of any object. So in complex demodulation, this ratio is fixed. So I decide from the start whether I want a good time resolution or a good frequency resolution or a trade-off between the two, which leads me to a very regular matrix, easy to analyze. But how about if I don't care about good time resolution in low frequencies, but I do care a lot about this for high frequencies? Yeah, then in wavelet analysis, the wavelets can be adjusted such that for each frequency investigated, an optimal trade-off is achieved. At least that's the theory. And how about if I want to include high frequencies in my analysis, but I'm worried that noise will compromise the connectivity results? With multi-taper, signal-to-noise ratio can be improved at high frequencies, but not for low ones. So in the end, there's always a trade-off that one has to live with. Moving on to connectivity methods. So for EEG-MEG data analysis, we have in general two types: functional connectivity measures and effective connectivity measures. Many connectivity measures are phase-based measures. This means they use the relative phase between two channels in the connectivity calculation. And in order to do this, we need the real and imaginary parts of the wavelets. Typical phase-based connectivity measures are coherence, imaginary part of coherency, phase locking value, and various types of phase lag index. And then there's a different family of connectivity measures, the Granger causality-based methods. And members of these are the Granger causality itself, the directed transfer function, and partial directed coherence. There are also others, but these are the ones that are currently implemented in our software. Yeah, coherence, to start with, is maybe the best known connectivity measure. It describes the amount of in-phase components in two signals at a specific frequency. We have the cross-spectral density matrix, SXY. So X and Y are the two different channels that we want to analyze. And it is normalized such that the final measure is somewhere between 0 and 1, or could even be 0 and 1. Not at the same time, I suppose. Yeah, and let's have a look at how that works. So generally, we have several trials that we are analyzing, and for each trial, we have computed the amplitude and the phase relationship between these two channels. So let's say, for argument's sake, that in one scenario, we have an amplitude ratio between the two that is always the same in the 5 trials here. So if we have a high amplitude in the red channel, we also have a high amplitude in the blue channel. If the low amplitude in the red channel is present, then also in the blue. And then furthermore, we have a phase relationship between these. And in this scenario, let's say that the phase is always the same. So in this case, it's always about 60 degrees or so between the two, if you imagine the phase being plotted around a circle here. So in that case, we have an ideal amplitude correlation and also an ideal phase relationship, which leads us to a coherence value of 1 between these two channels. The next scenario is that we have some sort of correlation between amplitude and phase. So usually when the amplitude of the red channel is high, the amplitude of the blue channel will also be higher, but not always. And the phase is, in this case, always in the first quadrant, but is not always the same. So then we have a correlation between amplitudes and also between phases, which means in the end that we'll have a coherence value that is still significant, but definitely smaller than 1. And finally, we have a scenario where we have a random relationship between amplitude and phase. And in that case, the coherence will be 0 or close to 0. So that's the way coherence works. And this was then refined in several ways. So let's just have a quick look at what else is on offer. We have the imaginary part of coherency, and this excludes coherent sources with 0 phase lag. And why is that done? Because that can reduce the effect of field that's spread due to volume conduction effects. So we simply look at the imaginary part of this cross spectrum, and this leads us to now a value that can also have negative values, so it can go from -1 to +1. And this has a positive effect because it can tell us something about the flow of information. So if the value of the imaginary part of coherency is positive, then the time courses x and y are interacting, and the time course y is earlier than x, which is probably equivalent to saying that if information is flowing from y to x. Then we have the phase locking value. So that again looks at the phase relationships, but totally discards the amplitude. So it's only interested in the phase relationships between the two channels that we are looking at. And again, it's normalized between 0 and 1. This again is a non-directional connectivity measure, so we can figure out if there is a correlation in the phase space between the two channels, but we cannot know which channel was causing the other one. Yeah, and for the phase-based measures, the last one I want to discuss is the phase lag index, which is a measure of asymmetry of the distribution of phase differences between two signals. So the phase lag index, PLI, uses the sign of the imaginary part of the cross-spectral density. And it is also normalized, so it does not give you the directional value. However, there's a couple of different flavors of it that we can use. And if we look at the parametric directed PLI, which uses a Heaviside step function, then we can actually determine which of the signals is leading in the phase relationship. So it's in that way a little bit similar to the imaginary part of coherency. And after all these phase-based connectivity measures, we also have a class that we call the Granger causality-based measures, which are a little bit different. So the Granger causality states that if past values of time series y of t contains information that helps in the prediction of time series x of t, then y of t is said to cause x of t. So this is really a different approach, and the measure is a logarithm of the unexplained variance from x's autoregression divided by the unexplained variance in the joint regression, which sounds pretty complicated. Let's just imagine that the joint regression is a better predictor than the autoregression. Well, in that case, sigma 2 will be smaller than sigma 1. So this ratio will then will rise. So Granger causality will become larger, meaning that y helps to predict the signal of x, less unexplained variance. Right. But in the frequency domain, it gets a bit more complicated still. So we can extend it to the frequency domain, and these are the formulae, but I think I'll skip going through that in more detail. But what you can see is that also the spectral density plays a role here. It just needs to be estimated, and then we get to the noise covariance matrix. So it's quite an involved technology. From this Granger causality, we can derive other measures. And there was two other measures that sound interesting. One is the directed transfer function that was introduced to reveal indirect information transfer between signals. And we can see on the plot here that the idea is that, say, if there's information transfer from J to I, it can happen directly, or it can happen via another route, and this should also be considered here. And in contrast, we have the partial directed coherence, which measures only the direct interrelations between the signals. So this will remove the indirect pathway from this estimation. So basically, you could say that DTF has a weak point because it cannot differentiate between the direct and the indirect connection, but that's just the way it's designed. So we're not finished yet, because we have talked about these interrelations of channels I, J, K, and of course, ideally, we would really only look at information exchange between neural generators in the brain, not so much about what's going on the scalp, where the channels I, J, and K may show us exactly the same brain activity, just propagated to the scalp. So if I look at sensor space versus source space, signals that I collect are usually collected on the scalp or some distance away from the scalp, even if I use MEG. However, now with OPM, we get close to the scalp again with the magnetic signals. And the skull acts as a strong insulator for electric currents, which means that at least in EEG, signals will be quite smeared and blurry once they get to the scalp. However, we have the opportunity to use spatial filtering that allows us transforming the data from sensor space back into source space. How does that work? Well, let's just have a quick look at how these currents are even generated. So neuronal current typically flows perpendicular to the cortex and creates dipolar fields. And the orientation of these currents can be radial with respect to an approximated sphere. So in this case, approximating the head surface by a sphere, or it could be tangential, or it could be none of the two. So if we're looking at a radial current, what does it do? It actually creates a widespread smeared voltage topography over the whole scalp with a negative maximum over the activated cortical sheet. So you can see here that you have the main part of the signal in maybe 4 or 5 electrodes in this scenario, but you also have some signal somewhere else from just one generator in the brain. Activity in a fissure would result in a tangential current. The sensor topography now has 2 maxima on the right, here in this top view, and these are 100% correlated with each other or anti-correlated. But none of the electrodes are close to the actual location of the neural current in the brain. And that's just the reality of measuring signals from a distance. So we see the signal popping up in these electrodes, but the ones that are actually closer to the activity will not show much signal in this scenario of a tangential current. If I look at the same signal with an MEG data, with an MEG sensor set, then the sensors pick up more signal in the location where the source is, but still it spreads over several sensors. Right, but if we know about underlying generators, either from source analysis or from the literature, then we can model each brain generator by one source, shown here on the right. And then we can apply a spatial filter to transform the signal from the scalp to the brain into a so-called source montage. So we have a source model. We create a source montage. We can also use an atlas for this, for example, AAL atlas or other atlases. We could use beamformers to create virtual sensors in the brain, and these can also become source montage sensors. Then we apply these source montages to our individual trials, and then we can do our time frequency analysis and, for example, temporal spectral evolution in source space rather than looking at sensor space where we have a lot of volume conduction effects. Okay, so that was quite a bit of theory bombarded you with. And one more thing is that we have a complete pipeline now, but an issue is now we maybe have too much information. So let's assume we have 15 subjects. We have 2 conditions that we want to analyze in these subjects. We maybe want to try out 2 different time frequency methods and 3 connectivity methods. Then we have identified 40 source channels that we are interested in. We're looking at 50 latencies and 25 frequencies, and then we end up with 9 million data points. That's a bit too much. So we need a tool that enables us to reduce the data in an easy fashion, to quickly compare different approaches, and to give us comprehensive overviews. And a solution for this is the upcoming tool, Bezier Connectivity 2.0, because we now have grand averages over subjects for the main trends. We can average over time and frequency ranges. We have a 3D view. We have a circular conic tone view, and we can also toggle through conditions, subjects, and the methods. Yeah, so let's have a look at this. Basically, all the concepts that I was talking about here are universal. They can be applied in several toolboxes already, and we'll have a look at the basic research pipeline here. So basically, what we are facing is that we need 5 steps to get to our connectivity. First, to load the raw data, select the montage, our source montage of interest, define our ERP or ERF paradigm. Then we'll launch phasor connectivity. We compute the time frequency transformations and then do the connectivity workflow in order to figure out what the connectivity is. And now I'd like to show you how that looks like. So let me start my phasor research first to get access to the data. This data I want to show you is from an experiment that we did in a collaboration in the Childbrain project. There was an audio-visual stimulation. In this case, there were Chinese signs that represented syllables, and these signs were shown to the participants, and also they listened to the syllables being spoken at the same time. So sometimes the spoken and the displayed syllables were the same, and sometimes they were not. So we had a congruent and an incongruent condition here. And the whole thing was recorded, as you can probably guess, with MEG. So here we have 306 MEG channels that shows the data, including high blinks here. And now the first thing I want to do is transform this data into source space. So actually, we're going to go to a user montage that is for this subject, the 44 channel montage. So there's 21 sources with 2 orientations each for the MEG, and also 2 sources in the eye fields to pick up activity that is simply due to eye activity. So how does that look like? Just show you a little bit in the montage editor what this is like. So we have these 23 sources altogether. For example, motor cortex, since there was a motor reaction required, heterogyrus for auditory, primary occipital, visual cortex, and fusiform area, and some others that may or may not play a role in this audiovisual integration. So this is my source montage that I basically put together from the literature, and now I can go to the ERP module to look at the conditions. So we have some simple conditions that simply summarize all the triggers that that create an auditory stimulus, and the ones that created just a visual stimulus. And then we had these congruent and incongruent events with audiovisual simultaneous stimulation. And for these ones, I want to now analyze the data. So yeah, we can always do an artifact scan, but this has already been done, and how to do this is explained in the different tutorials. So we'll just move on to the coherence tab here, and we're going to analyze these just a shorter epoch, because we don't want to wait for computation for a long time here. So we're going to have the congruent and incongruent conditions, a little bit shortened for faster analysis. And the first thing that the program does is to write this data to disk and then start with the connectivity, so we can directly pick it up for time frequency analysis. This should now start with the connectivity, but since the released version is still the old version, not version number 1, I'm going to cancel this now, and instead I'm going to try and show you the new version, which I start now, and then I can start a time frequency analysis workflow. And I'm just gonna go through the congruence for the moment. So just start with the congruent condition, and that should be directly listed in my export. So here, this was the first one I exported, this congruent one, and I can load it, and I can see I have 89 trials that survived the artifact scan and 44 channels in my data. Then I go to the next step, and here I can sort of review my trials again, which I don't need to do, and I can define my low and high frequency cutoff. So I'm just going to work with between 2 and 40 hertz here, because that is the main activity of interest that I expect. And then I run the time frequency analysis. And finally, I get my plot of the temporal spectral evolution. So let me zoom in a bit. I don't need the eye fields at the top. I just need to look at the other channels. I can click on any of these channels to magnify them. And on the left side, I can always see the average of this channel, and on the right side, I can see the change in spectral activation over the time and frequency. The color map can be adjusted, so there's, for example, the blue to red color map, so it's kind of your individual preference which one you like to work with. I'm a bit old school, so I still like the old one here, but many people told me this is actually a bit outdated and we should go to the other one. Anyway, that's totally up to you. So we can see that there's various channels where we have quite a lot of activation that follows the stimulus. For example, occipital cortex, but also in the fusiform area here in the posterior superior temporal gyrus. So let's see what we find in the connectivity analysis. So first I need to save this as a project, and I just call it demo project here. Maybe remember that the congruent stimulus. And then I'm back with my workflow selector, and I can now select the connectivity analysis workflow. And the first thing here is to pick the methods I want to try. And right now, for time reasons, I will not do the Granger-Casali because that actually is computationally quite expensive. But I do want to have a look at the phase lag index and coherence, imaginary part of coherency. Then I go next and next, and then I can just pick up this project that I just saved, and gives me the summary again. And I can just go through and run connectivity analysis. This should be fairly fast and should show me then the overall view between the different channels, so the 44 channels that I have identified. And basically, I can now see the coherence of all channels with all channels in one large plot. I'm going to hide the diagonal because that's just the self-spectrum of the channels, and also zoom a little bit into this display. And then let me go down to the bottom, zoom a bit more, also scale up a bit. And then I can already see that some channels have a very high coherence, especially at high frequencies, and this is exactly the issue with the coherence, that in this case I don't have the volume conduction as such, but I have the problem with the spatial filter, that noise that I haven't modeled will distribute in the same way over various channels and then come up as a mock coherence. So I should focus a bit more on the lower kind of activation. So for example, I can see this channel here, if I click on any of these display channels, I see the large plot that in the fusiform, I have some activity between fusiform and the posterior superior temporal temporal gyrus. And let's then have another look at this. And one thing I can also do is I can average over time and frequency range. So why don't I check this box, and then I can say that I'm mainly interested in what happens between 150 and 200 milliseconds after the stimulus. And then I can already see the different plots here. So I can now see which frequencies are mainly active in terms of coherence between these channels. And I can go further and also average over frequency range. And if I do this, then I actually only get one value per channel pair, which is then the average over this time frequency bracket that I have chosen. So let's say I want to look at 4 to 7 hertz. So this frequency band here, and that now I can zoom out again to kind of get back to my standard plot, which is now basically the full conic tone plot for this particular time and frequency range that is individual for this subject with this task. And the same thing I can now look at in the 3D mode. So let me just click on the 3D mode here and now see the connectivity in the brain itself. This is with a threshold of 0.5, so it only shows me connectivity coherence that's larger than 0.5. And now I can also go directly to the conic tone view. And this conic tone view now gives me the full overview of the connectivities, basically arranging these sources, my source channels around the circle, and yeah, giving me an overview of the connection at one glance. And now I can play with the frequency range again. For example, let me change it to 8 to 12 hertz. And I can see how the conic tone plot changes directly. And maybe I can notice that most of the connectivity here is within the hemisphere. So let me now go back to the 3D mode and change the method up here. So I've looked at coherence. Now let me look at the phase lag index instead. And now I need to lower the threshold a bit because it doesn't have such high values. And I can see what happens now is that I actually get much more interhemispheric connectivity. And one reason for this could be that the phase lag index in particular looks at signal that's not totally synchronous. So there's not zero phase lag here, but it will be more of a phase lag, and this then favors the connectivity between hemispheres. However, I can also still see some activity along the left hemispheric side here. So let me go back to the conic tone view. So here I can see that indeed I have both. I have the interhemispheric and also the intrahemispheric connectivities here. And now I can go back to my 4 to 7 hertz range and see what stays, which connectivity I have available there. And there I have a lot more happening at this lower frequency range. But again, I have a mixture of the left, mainly on the left side compared, and also the hemispheric stuff. So going back to the 3D mode and maybe raising the threshold a bit. You can see that, so now I've got less connectivity, but this these left hemisphere still remains. So obviously, I can already conclude that I think there's something more going on in the audiovisual integration on the left side compared to the right brain hemisphere, which is also pretty much in line with what we would expect, because some of these particular specialized brain areas are on the left. So let's just have a look at the channels that are involved here. There's a TVSA02. And if I'm interested in a channel like that, then I can also simply select this from the display here, and it's connected to the supratemporal gyrus, orientation 2. Yeah, so now we can see this is actually a strong connection, and let me unaverage these again. And then I can see also quite interesting that I'm just at the beginning of this connectivity here. So it actually gets stronger a little bit later in time. So this is something that obviously is important in the integration, but is not active straight away, but a little bit later in time. So I can very, very interactively play with this data and understand it, and try different methods. And let me just, the last thing, also look at the imaginary part of coherency. And this also gives me extra information, because now I can see that this, the direction of flow is actually from the supratemporal gyrus to the TVSA. So this is something I couldn't see from the other methods. Good, so that was the analysis. Okay, just of course I could go much further. One thing I can also do, forgot to mention, is export the whole thing. So I could export any of the these three windows, the main window, these ones at a resolution of my choice. I can also export the complete connectivity data, and this is important for later downstream analysis. Or I could create a video of my connectivities over time. Yeah, so this is all stuff worth playing with. So now let me just finish this project and then go to my last topic for today. So I'll just call this project on, and then go back to my presentation. And just one more thing that is worth mentioning is, I think I'm in the wrong mode right now. Yeah, one thing that's worth mentioning is that I can also use the batch processing in my Blazar research, and that will then allow me to do multi-subject analysis on a basically an arbitrary number of subjects, and I can prepare all the data in the batch for connectivity, save all this data, export all the data epochs for connectivity, and then continue the batch processing through Blazar connectivity, and also export the data, for example, for a final look at Blazar connectivity. And this Blazar connectivity, Blazar statistics, I'm going to say. So I can export it to Blazar statistics, and then I can go through that workflow, choose a statistical test, load the exported results, and calculate the cluster permutation statistics. So let's just have one last look at how that works in Blazar connectivity. And this will again require me to start this program. And now I'm going to do a time frequency analysis on a number of subjects. So I have two conditions now, and the conditions are, of course, my congruent and my incongruent condition. And I can load the data for the congruent condition, which has been imported by Blazar Research, and I can, in the batch for export, I can specify which folder to export to. So all my congruent ones are here, and in this case I have 9 different subjects. And now the data are loaded. And I can do the same for the incongruent subjects. So if I did the batch more elegantly, I would export them to different folders, and it would be even easier. But it's still quite easy to pick them. And I can see up here the number of trials that were found in these different data files. And also in the incongruent case. So now I have loaded all my data, and I can go next and directly go do the time frequency analysis for all of them. So now what I see in my overview is actually the grand average on the left side of all the these source channels. And so, for example, if I look at the this occipital channel, I can see this is actually very, very smooth in the grand average compared to the individual data. Yeah, and I can now again do. Let me just do maybe a shorter. Just go up to 25. Since we're running out of time here, it's just for demo purposes, and I'm going to run this analysis on these 9 subjects with 2 conditions. And it doesn't take very long, and then I have my time frequency project finished, and I can use that also for connectivity analysis. So here I have my grand average again for the temporal spectral evolution, and the cool thing is I can now just toggle through the different subjects, and I can see how it is different with the different subjects. So you can see there's quite a bit of variability, and also I can toggle the conditions. So I can also swap between congruent and incongruent case directly on the fly. Okay, and let me finish this project, and I'll just call it demo project 2 conditions, 9 subjects, and go to the connectivity analysis. And I'm going to choose the same 3 methods again. Pick the project. This now takes a bit longer to load the data, of course. Yeah, what I didn't tell you is from the time frequency already, I can also export this time frequency data for statistics analysis, and we have a way of doing the export of the whole project data together, and this will organize it in the subfolders so that you can directly pick them up really easily in Visual Statistics. So here we have our data loaded, and we just now need to do the connectivity analysis. It's quite fast. And the longest time is now spent on calculating the visualization for these 44 channels times 44 channels. And here we are. So this is our grand average of the congruent condition. And I'm simply going to pick the same channels again. So I have my fusiform with the posterior superior temporal gyrus, and you can already see that there's still an effect in the grand average, but it's not quite as clear as maybe we had it before. But nevertheless, we can see it, and we can also look at the 3D mode. And now we need to go down a bit with the threshold because of the grand average. And now we can see compare the conic tone in the congruent condition with the one in the incongruent condition. So here we have the grand average of the congruent, and here we have the grand average of the incongruent. And what we can also do, of course, is simply toggle through the different individual data, and we can see there's indeed some variability. Of course, this will also be across because time and frequency will not always be exactly the same. So it would be advisable now to perform cluster permutation statistics to see are there any effects when I compare the grand average that will survive this comparison of the congruent and incongruent using the average data sets. But I think this is scope for the next webinar. We will not solve that today. And for the moment, I would like to go to my final slide. And thank you very much for your attention. Mention the scientific contributors: Robert Spangler, Jaehyun Cho, Avinash Pant, Wei-Young Xu, and Jarmo Hämäläinen, who recorded the data. Michael Shirk, Patrick Burke, Dieter Weckesser, and Nicole Wille, who did a lot of groundwork for the source montaging. And now I would like to see if there's any questions. So I'm not sure if there was, let me just see if there was questions that can be answered or have already been answered. Maybe Robert, can you unmute yourself and let us know what the most important questions was? There was one here. I can see at what point can you change montage? You have to start over if you want to change montage. So yeah, the montage is actually at the beginning of the pipeline. So indeed, if you want to look at a different source montage, you will need to go back to the raw data and apply that montage to the raw data and redo the export for the time, frequency, and connectivity workflow. And then I think there's also a question about resting state. So do we have a chance to analyze resting state data in Visual Connectivity? And yeah, that can also be done. We have a pipeline for this. What we do in Visual Research is that we kind of put regular triggers of a certain epoch that you want to include in your resting state, and then we do the time frequency. We need the time information at that point to figure out the phase relationships between channels, and we keep that until we've computed the connectivity results, and then you can simply average over the whole time and then get your resting state connectivity over the whole epoch. So we have a pipeline for this and some information material that we can send you upon request. So this is the two questions that I could see. If you like, please I will still be here for a couple of minutes. So if you want to add another question to the chat, feel free. Give me 1 second.
Hey, Harald, can you hear me?
Oh, now I can hear you, yeah. Mm-hmm.
Oh, great. I just chose a different microphone. So there was another question. So thank you very much for your talk. There was another question regarding the differences between complex demodulation and wavelet transform. Maybe you can talk about that a bit.
Yeah, so complex demodulation is the method that I just showed, which is the fastest to compute. It basically has a fixed relationship between the the time and the frequency resolution. Wavelet, in contrast, has not got that. So the wavelet tries to optimize the relationship between time and frequency, and so that, for example, for low frequencies, the wavelet transform will give you a good frequency resolution, but a bad time resolution. And for high frequencies, you will get a better time resolution, but again, in contrast, a bad frequency resolution. So yeah, I could actually maybe run this really quick. Just go and close this and do an example of a joint analysis of to start with our example that we just had. So I had this CNH, and we can do both wavelet and time frequency and complexity modulation. And here I can adjust the wavelet parameters. So, for example, I could choose the width, but that's not so important. But the number of oscillations has quite an impact. So let's put it to 3 for the moment, and keep the time frequency sampling for the complexity modulation. And now I can analyze the same weight data set in the 2 different types. So let's have a look. For example, let's go for this empty. How much was it? Yeah. So let's look at this one. This is the complexity modulation result, and now I can switch to wavelet. So I can see that the wavelet here has a slightly different shape. So basically, the higher the frequency, the better the time resolution, and it kind of homes in on this time around 150 milliseconds. And if I look at the complexity modulation, it's kind of the frequency resolution is potentially a bit better, but the time resolution is much worse here. So yeah, so the wavelet can give you some benefit in terms of giving you a better trade-off between time and frequency. Also here, I think in this SMG. Yeah, so in this case, it's a bit more focal, or gives you a better shape. And it doesn't have only advantages, though. I think it's also a bit more prone to noise at higher frequencies compared to the complexity modulation, which is maybe a bit more sturdy, let's say. But I think it's worth trying them out. And luckily, we have this option. We can simply activate both of them and then see what the effect is on the connectivity. Yeah, thank you.
Thank you very much for your answer, Harald.
Yeah, thank you, Robert.
I have one more question for you. Do you want to handle one more?
Oh yeah, sure, go for it.
It's about the data export from time frequency analysis and also from connectivity analysis, whether it's possible to export the results and how you can eventually use them for statistical analysis, for example.
Okay, yeah. So the export is done via the export menu. We have our results. We have the single trial. Yeah, we can do the single trial time frequency data. So you can actually then do an in-subject analysis if you like. And we can do the average time frequency data. So this makes sense if you want to have a group of subjects and you want to do the statistics on that. So you simply press that button and you go and export it. It'll come out as a TFC format, and the TFC format can then directly be read into business statistics. And I'm not sure if this, maybe Robert, you know this better than me, if this version already supports the batch export of, or that's maybe still not fully completed, but will be completed in a few weeks before we release the product.
Yeah, so the version you're using at the moment is still the 2.0 beta, and it's under development. So the export functionality that you're referring to is not available 100%, I'd say.
Yeah, yeah, but I think it's close to completion. So basically what we can then do is we can open our data set, and then we just go to export. Then it'll batch export all the different subjects into different subfolders, and this will directly be picked up by the business statistics. So I think it should be hopefully very convenient to then go to the final step of analysis of your group experiment. Yeah, and yeah, one thing is maybe I should mention is if you are interested in this upgrade to Bezier connectivity, we have a special offer ongoing till the end of the year. So please get in touch if that is of interest to you. So yeah, here we would go to the results and then project results, and this will then trigger the actual final export of everything. So pretty straightforward, I think. Okay, now we're actually also at the end of our allocated time. So I would like to thank you very much again for dialing in, listening, and giving your input. And I hope to see you soon at some other event. And I hope you have a great holiday period. And yeah, see you soon. Thank you.
Thank you very much, Harald. Cheers.
Thanks, Robert. Bye.